Hello everybody, welcome to our predictive analytics session. We are continuing with neural networks and deep learning. It's part 4. In last session, we have installed CUDA toolkit, QDNN, PyTorch and NumPy. In this video, we'll move into Python, and in this session, we'll learn how to implement convnets using PyTorch. Session information is implementation of convolutional neural networks using PyTorch on CPU. Let's come to the Python implementation. Here you open CMD, type Jupyter Notebook, click on new. When Jupyter Notebooks you will find it will, then you have to click on this new, then select Python 3, rename the file as convnets, rename. Let's start. Import torch, this imports PyTorch. Import torch.nn as nn, this imports nn module from PyTorch. Import torch optim as optim from torch autograd, this imports our optimizer or loss function. Recall, in our last session we have discussed it. Next, import variable from torch utils data, this imports variable which is useful for computations. Next, import data loader from torch utils data, this is used to load the dataset. Import sampler, this helps in sampling of data. Import torch vision datasets as dset, this will import the datasets for use like CIFAR10, ImageNet, etc. We'll be using CIFAR10 in this learning session. Import torch vision transforms as T, import NumPy as NP. We'll be applying various transformation to improve the quality of our dataset. As you will see, import timeIt, this is used for various time functions. Then press run. You may get syntax error, invalid syntax. It may be due to spaces. Now run. You can see this type of errors you may face and how to eradicate this kind of errors. So now there is no error. Now we need a tool which will help in loading our dataset. Class chunk sampler dot sampler is the command. Then def init in bracket self num samples start is equal to 0. It will sample elements sequentially from some offset. Arguments are number of samples, that is number of desired data points. Start this offset where we should start selecting from self num samples is equal to num samples. Self dot start is equal to start. After that def iter in bracket self, this return our iterator object. Return iter in bracket range self start comma self start, then self num samples bracket closed. Next def len in bracket self, this will return the size of the data set. Return self dot num samples. Next num train is equal to 49,000. This is our number of training examples. Next num val is equal to 1000. This is our validation set which will be used to test accuracy of our network. Cipher 10 train dset cipher 10 you write the location in desktop cipher 10, then train is equal to true, download is equal to true, transform is equal to T2 tensor. Close your bracket. This will download cipher 10 dataset. Dset calls cipher 10 which accepts location where we have put our dataset in. Training is set to true to download. If it's true and we finally transform our data into tensors instead of NumPy arrays. Tensors provide a lot more functionality than NumPy arrays. Hence we have transformed the data from NumPy to tensor. Next, loader train is equal to data loader cipher 10 train batch size is equal to 64, sampler is equal to chunk sampler in bracket num train comma 0. This will load our training examples and store it into loader train with 64 batch size, and sampling is done as defined in chunk sampler above. Next, cipher 10 val is equal to data d set cipher 10, import from your location, that is desktop cipher 10, train is equal to true, download is equal to true, transform T to tensor. Similarly, we download our validation dataset. Next is loader val is equal to data loader cipher 10 val, batch size is equal to 64, sampler is equal to chunk sampler, num val comma num train. This will load our validation dataset. Next, cipher 10 test is equal to d set dot cipher 10 you can copy and change the command and put the same location of your data, that is desktop cipher 10 comma train is equal to false, download is equal to true, and again transform is equal to T2 tensor. Next, loader test is equal to data loader cipher 10 test, batch size is equal to 64. This will download and load our test dataset. Let's run this. This will take some time, but after files are downloaded, they will be stored as cache, so it will be faster the second time you do the process. If files are already downloaded, it shows files already downloaded and verified. For now, we are going to use a CPU friendly data type. Later we will switch to a data type that will move all our computations to GPU, and hence the measuring capability will speed up. However, GPU based CNN implementation will be featured in our next session. Here type D type is equal to torch float tensor. This is the CPU data type. Print every is equal to 100. That means we'll be printing our training loss every 100 iterations. Def reset in bracket m if has attr in bracket m reset parameters colon m reset parameters. This is a small utility that we will use to reset the model if we want to reinitialize all our parameters. Next, press run, and let's start looking at a simple model. We'll use flatten function. Remember that our image data and more relevantly our intermediate feature maps are initially n cross c cross h cross w, where n is the number of data points, c is the number of channels, h is the height of intermediate feature map in pixels, w is the height of the intermediate feature maps in pixel. So last one is the weight, that is w is the weight of the intermediate feature map in pixels. This is the right way to represent the data when we are doing something like a 2D convolution that needs spatial understanding of where the intermediate features are relative to each other. When we input data into finally connected layers, however, we want each data point to be represented by a single vector. It's no longer useful to segregate the different channels, rows and columns of the data. So we use a flatten operation to collapse c cross h cross weight w values per representation into a single long vector. The flatten function first reads in the n, c, h and w values from a given batch of data and then returns a view of that data. View is analogous to NumPy's reshape method. It reshapes x dimensions to be n cross something, where something is allowed to be anything. In this case it will be c cross h cross w, but we don't need to specify that explicitly. Now class flatten NN module, next def forward, self comma x nh nchw is equal to x size. This reads in nchw format, return x view n minus 1. Finally we flatten. Here's an example. We have to first press run and then we'll start with an example of a convolutional neural network defined in PyTorch. We'll try to understand what each line is representing, remembering that each layer is composed upon the previous layer. We haven't trained anything yet, that will come next. For now we want all of you to understand how everything gets set up. NN sequential is a container which applies each layer one after another. Fixed model base is equal to NN sequential NN conv d, conv 2d we have to write in bracket in channels, specify it with 3, out channels is equal to 32. These numbers we have put as an example. Kernel size is equal to 7, stride is equal to 1. This is our conv layer with 3 input channels, 32 output channels, kernel of size 7 and stride as 2. NN ReLU in place is equal to true. This ReLU is nonlinearity. Hope you remember. Next, NN batch norm 2D, num features is equal to 32. This is the normalization layer. Then NN is max pool 2D, in bracket kernel size is equal to 2, comma size is equal to 2. This is the pooling layer where we have put the size of our kernel as 2 cross 2. Recall from our last session. Then we type flatten in bracket. That means we flatten the image before we send data to fully connected layers. Then NN linear in bracket 5408 comma 1024. This is our fully connected layer with 5408 neurons. NN dot relu in place is equal to true. Then NN dot linear 1024 10 output neurons which represent individual class cores. Next is the fixed model base. So we basically have implemented this architecture followed by fully connected neural net. Now fixed model is equal to fixed model base type D type. This set everything up to our CPU data type. Next is the loss function. Loss Fn is equal to Nn cross entropy loss type D type. Will be using cross entropy loss for this example. Optimizer is equal to optim RMS prop in bracket fixed model parameters LR is equal to 10 e to the power minus 2. We'll be using RMS prop optimizer, which will be helpful for reducing loss quickly. Then press run. Type error, got an unexpected keyword, argument size. Go to the, if you find this kind of error, you check the size part and correct the as it will be stride, you can see it. So this kind of error may occur initially, and then you run and then you find it's okay. So you are also learning constantly to also remove the error, and with more practice you will find error will be nullified. Next, type. Now let's quickly check whether we have set up everything correctly or not. We'll do this by sending some random data through this network. X is equal to torch rand n. 64, 3, 32, 32. Type, D type. We initialize some random data and store it in X. X var is equal to variable X type, D type, convert X into CPU data type and PyTorch variable. Next, ANS is equal to fixed model in bracket X var. We feed our X to the model. NP array equal in bracket NP array in bracket and size comma NP array 64 comma 10. This is checking the dimensions of our output with the expected output. If this is returned as true, so this you can check by pressing run. If this is returned as true, then congratulations, everything is working as intended. Otherwise, you should rewatch this learning session and find out what went wrong and correct it. This is all for this learning session. In the next learning session, we'll see how to use GPU for faster computations and start training our network. Thank you. Feel free to contact us for clarification at the following email address.